Oh, hello, hi. Am I audible? Hello, hello, hello. Yes, okay, fine. So, hi, this is week three of the course, Mathematical Methods in Physics, second part. Today we'll be looking at problems related to the week three content, and I'll be mainly focusing on the third assignment of this course. So, week three, assignment three. Okay, before that, is there any doubt with respect to the previous lectures, the previous assignments, or anything of that sort? If there are any doubts, you can ask right now, or else you can proceed with the third assignment. So, are there any doubts? All right. Okay. So, let's proceed with the third assignment. So, this is the first problem. I'll just copy from here. So, the question says evaluate the integral, and we have this expression 2x dy minus 3y dx, and this integral is over a contour. Now, what is the contour? The contour is around the square with vertices 0, 2, 2, 0, minus 2, 0, and 0, minus 2. And we're supposed to do it directly from the first principles. Okay, so let's do it. So suppose I draw the axis here. The second part is use the Green's theorem to check your answer. So we're supposed to verify our answer using Green's theorem. So first let's do this. Okay, so this is my axis. This is x axis, this is y axis. Um, and I'll draw a square. All right, so why did I draw like this? Because they have said that the vertices are at say 0, 2, 2, 0, minus 2, 0, and 0, minus 2. These are the vertices of the square. So that's why I've drawn a square in this manner. All right. So now we're supposed to calculate the value of the integral along this contour. So assuming that the contour is in this direction, it's going like this, right? So let me name this also A, B, C, and D. So from A to B, what's the integral? I is equal to integral over this contour 2x dy minus 3y dx. So this is the integral we're supposed to evaluate. This is the integral we're supposed to evaluate 2x dy minus 3y dx. Okay. So now uh, for AB, so basically now I'm saying that I'm going along this path from A to B. I'm going along this path right now. If you can see, I marked this in green. I'm going from A to B right now. So in this case, uh, what is the equation of this line? What is the equation of line AB? Equation of line AB. What's the equation? The equation is y is equal to simply mx plus c, right? So y is equal to, the slope would be minus 1 minus x plus c. The y-intercept is 2, so minus x plus 2. So y being equal to x, yes. This is the equation of line AB. All right, you can just, you know the 2 points, you can just use that and get the equation of line. Nothing fancy here. So now dy, because this is the path along which we are going, so we can get a relation between dy and dx here. So dy is equal to simply minus dx. That's it. Okay. Now let's put it here. Integral 2x 2x dy, which is minus dx, minus 3y, and dx will be minus dy, minus dy. Sorry, we are just doing from a to b, from ab, along ab. This is the integral. So along ab, what will this be? X goes from, in this direction, as x goes from 2 to 0. So 2x dx with a negative sign goes from 2 to 0, 2 to 0, minus 3y plus 3y dy, because minus minus becomes plus. And here y goes from 0 to 2, 0 to 2. So what does this become equal to? This becomes equal to minus x square by 2, 2 to 0, plus 3y square by 2, 0 to 2, so is equal to 4 by 2, which is 2, plus minus x square by 2 and 3y square by 2. It goes from 0 to 2. So this becomes 4, 3 into 4, 12 by 2 is 6. The second is 0. So this becomes 8. Sorry, different. And 0 is 0. So 3y square by 2. 4, 3 into 4, 12, 6. And this is okay. Y is minus x plus 2. Dy is minus dx. So here for 2x dy, plus, which is fine. Oh, okay, okay, okay. This is x square only, not x. Not x square by 2, because there is 2x already. So what I end up with is 4 here, right? So this becomes 10. My bad. So what I'm getting here is 4 plus x is equal to 10. My bad. All right. So this is along AB. Then similarly, we'll also do along BC. I is equal to integral along BC 2x dx minus, sorry, 2x dy minus 3y dx. So this is what we'll do along. Now I'll go along BC. this, if you can see, I'm marking it with a blue line. Uh, okay, so along BC, what's the equation of the line? Equation of line BC. This is y is equal to this. The slope is 1, right? Y is equal to mx plus c. M slope is 1, x plus 2, because the intercept is 2 here. Sorry. So upon putting y equal to 0, I'll get x equal to minus 2, which is yes, that satisfies both the points. All right, so dy becomes equal to dx, and again we can solve this integral. Because the direction of BC is downwards, so we'll take the x and y limits accordingly. That we have to be careful with, of course. So 2x dy will become dx, and what's the limit of x? X goes from 0 to 2, because here you can see I'm going along BC. So at B the value of x is 0, and at C it's minus 2. Sorry, it goes from 0 to minus 2. Minus 3y dy, dx becomes dy, and here the value of y goes from 2 to 0. It's at some higher value, then it goes lower, 2 to 0. That's the direction of y. Okay, so now solving this, x square 0 to minus 2 minus 3y square by 2 to 0. This becomes equal to 4 minus 0 minus 6. So this becomes equal to 10 again. So I got the answer 10 here. I'm getting the answer 10 here too. Now for the third and the fourth contour, I is equal to, now for CD, line CD, y is equal to, I was going like this, it's minus x minus 2, because the y-intercept here is minus 2 at D. So minus x minus 2, therefore dy is equal to minus dx, I is equal to x square, sorry, I have already integrated, I can just 2x dx with a negative sign. What is the limit? It goes from, x goes from minus 2 to 0, minus 2 to 0, minus 3y, dx becomes dy with a change of sign, and y goes from 0 to minus 2, 0 to minus 2, right? Y is going from 0 to minus 2, this is going from minus 2 to 0. Yes, minus 2 to 0, 0 to minus 2. Yes, these limits work, is equal to, this becomes equal to x squared again as usual, and I'll get minus 4 here, minus 4 plus 6, minus 4 plus 6 is equal to 2. So the third line gives the answer 2, and I'll just check it once. X squared 0 minus 2 gives me minus 4, because minus 2 is at the lower limit. Okay, so now along line DA, the equation of the line will be y is equal to x minus 2. So therefore dy is equal to dx. I becomes equal to integral 2x dy becomes dx. The limit is 0 to 2, right? The limit of x becomes from d to a, 0 to 2, and y limit becomes minus 2 to 0, minus 3y dy integral minus 2 say 0. So again x square, this gives me 4 here, minus, so there's a minus sign here outside. I'm making some small stupid mistakes. 4 minus minus 6, even this becomes equal to 10. So all the answers here, I had made a small mistake. I had not considered the negative sign here outside. So if I consider that, this also becomes plus 4. So this is also equal to 10. So basically, all the results are equal to 10, uh, and the entire integral, the entire contour integral over ABCD 2x dy minus 3y dx is basically 10 plus 10 plus 10 plus 10, so is equal to 40. That's my result. So we get the answer as 40 here. We now have to use the Green's theorem to check this answer. Okay, so what does Green's theorem say? If I have a function of the form u dx plus v dy and it has a contour integral uh, over some contour, so that can be written equivalently as um, it's del u by del y. I think I just confirm that. Okay, so it's del v by del x, right? Del v by del x, right? Minus del u by del y into dx dy. It converts it to a surface integral. A line integral around a particular closed path is converted to a surface integral over the surface which is enclosed by this path. So that's Green's theorem basically. So now using this theorem also we'll try to solve this. What is v here? V is equal to 2x, u is equal to minus 3y. That's our u and v, right? So therefore del v by del x is equal to 2. Del u by del y is equal to minus 3. So 2 minus of minus 3 dx dy integral. So this is simply the area of the square that we are considering. So this is basically 5 multiplied by area of square. I hope there are no doubts here. This is simply integral dx dy, and the surface that we are covering is the surface inside this contour, which is a square. So integral dx dy is basically telling me that I have to evaluate the area of the square. So 5 into area of the square is my answer. And what is the area of the square? Area of the square is one side length is, this is one side length, which is 2 minus 0 plus 0 minus 2 the whole square, square root. This is 2 root 2. The side of the square is of this length 2 root 2. So area of the square is simply 5 into 2 root 2 square is equal to 8 into 5 is equal to 40. So Green's theorem is also giving me the same result. So that's question number 1. Is there any doubt here in this one? This is a simple straightforward contour integral calculation. and we just verified it with the Green's using the Green's theorem. There is just algebra here. There's nothing more. Any doubts? Okay. You did follow what I did, right? You did follow the steps. You did follow the steps, right? Could you follow the steps? Yes. Okay. Okay. Fine. Okay. So that was question one. Let's move on to the next one. All right. So evaluate the following contour integrals by direct integration. There are two integrals given here, and we have to perform these contour integrals along three paths. So this integration goes from one is going from 0 to 1 plus I. So there can be many paths. So suppose this is my, let's draw it better. Suppose this is my complex plane. So this is 0, 1, I. So this is basically 1 plus I. So there are many ways to reach this point. I can choose any of these contours, right, to reach this particular point. So to evaluate this integral, we have to choose a particular path. So generally, if the integral is path dependent, the path has to be specified. So in this case, they are already telling us that we are supposed to follow the paths used in lecture 24. So in lecture 24, there were three kinds of paths used. One was, I'll draw it with different colors. So one was this path, if you can see in green. So this was one of the paths. Take a lighter shade of blue so that's visible. All right. The second was this path, and there was the third path, which is this one, directly from the origin till 1 plus I. So this is path 1, this is path 2, and this is path 3. So these were the three paths used in lecture 24 that is being mentioned in the question. So now they're asking which of the following statements are true. The first statement is, only one statement is true, by the way. So which of the following statements is true? I1 is the same on all paths, but I2 varies for different paths. So there are two functions I1 and I2. I1 is an integral of the function z square minus z, and I2 is an integral of the function mod z square. So we are supposed to verify which of these statements are true, whether I1 is same on all paths and I2 is also same, or whether I2 is different, I1 is same. So whatever the possible four combinations are given as options. So let's check that. Okay, so here, because this is your assignment, I'll just solve for I1, and I2 you can do it yourself. Okay, so let's do this for I1. So when I'm following this path, path 1, for I1, I'm doing it for I1 only, along path 1. So along path 1, firstly we have the first part of this path is along the real axis only. So in that case, z is equal to, so in this case, z is equal to simply sum x plus I into 0. This is how we can write uh, z along this path. Along path 1, let's say this is A, this is B, this is some C. So this is along OA. So I'm writing z is equal to x plus I0 along OA. All right. So the equation is this: z square minus z dz. Here we are going from 0 to 1 only along x. Z is equal to 0 to z is equal to 1. Only the real values. All right. And z we can write as x, simply x. That's what we realized. So this is equal to, it is 0 to 1, x square minus x dx is equal to 0 to 1. No, I can just perform the integral here itself. X cube by 3 minus x square by 2, 0 to 1 is equal to 1 by 3 minus 1 by 2 is equal to minus 1 by 6. 2 minus 3, 6. Yes. Okay. Now z is equal to, x value remains fixed now. If I'm going along this path in the vertical direction, what I did was I went from O to A till now. Now I have to go from A to B. So A to B is a path where x is going to stay constant, x is 1 only, and y will change, right? So z is equal to 1 plus I into y, where y will go from 0 to 1. So that is my uh, path, the z value along the path basically. So now I'll perform the integration again. The integral is z square minus z. So what is z square here? Z square is 1 minus y square plus 2iy minus z minus 1 minus iy into I dy, because dz is equal to I dy. Right. And y goes from 0 to I. No, no, no. Y goes from 0 to 1 only. I have taken y to be the real part of, sorry, y is the imaginary part of the number. So y itself as a number is going to be real. So this is going to go from 0 to 1 only, not 0 to I. Right? Is that understood why I took the limits like this? So, okay. Y minus y cube by 3 plus I y square by 2 minus y minus I y square by 2. Actually, for this one, there is no divided by 2. This is it. So y gets cancelled, of course. Mm, this goes from 0 to 1. So this is equal to minus 1 by 3 plus I minus I by 2 is equal to minus 1 by 3 plus I by 2. That's my answer. So, okay. So the all in all the answer is along OA, the integral is minus 1 by 6. Actually, it's not OA. It's along OAB. The whole integral is minus 1 by 6, which is along which is for the part OA, and then minus 1 by 3 plus I by 2, which is for the path AB. So the total becomes minus 1 by 2 plus I by 2. That's the net result. Along the path OAB, this integral yields minus 1 by 2 plus I by 2. Now we have to check for any other path. We can choose, say, maybe directly path 3, or maybe we can choose path 2. Okay. So I am giving you an idea. Because I am giving you an idea, I am not going to evaluate for both the all three of the paths. I'll just choose another path. Maybe I'll choose path 3 directly, and that will be verification enough for me. But while you are solving for practice, you should solve for all three paths, and for the next integral also you have to solve for all three paths. So for your own practice, you have to solve this much. I am showing you only along path 3 now. Along path 3, y is equal to x. Therefore, dy is equal to dx. This is my path 3. Okay, so z square minus z dz is my integral. I is equal to integral z square minus z dz. And this goes along this path from 0 to 1 plus I. From 0 to 1 plus I, right? But along path 3, yeah. So this becomes equal to integral z is x plus iy, which is, so z square is x square minus y square plus 2i xy minus x plus iy. Dx plus I dy. So because z is equal to x plus iy, so dx has to also be dx plus I dy. Dz is equal to dx plus I dy, right? Okay, so let's go ahead. Mm, X goes from 0 to 1 and y also goes from 0 to 1. Both x and y are same because y is equal to x is the equation of the line which we are following. So let's do it. X square minus y square becomes 0. Any doubts? Yeah, yeah. Tell me. Sorry. Along path 3, you're saying the value is y minus x. Y is equal to x. Along this path, y is equal to x. Yes. Yeah. Uh, yes. Z is equal to x plus iy. So basically, when I'm going along this path, z is equal to x plus iy. So x and y themselves are real values, right? Yeah. Tell me. Yes. Z is equal to x plus ix. Z is equal to x plus ix. That's what it becomes. Yeah. So here I have not substituted x is equal to y till now. Now I'll put it in. Right. So what does this become? X square minus y square cancels out. I get 2ix square minus x plus ix into dx plus I dx. Okay. And this integral goes from, where does x go from? X goes from 0 to 1. So this integral also goes from 0 to 1. So let's solve this. 2ix cube by 3 minus x square by 2 minus I x square by 2 plus minus 2. I'm putting I into I is minus 1. So 2x cube by 3 minus I x square by 2. There's a negative sign and I, so plus x square by 2. Yes. So this is the integral, and this goes from 0 to 1. Even this one goes from 0 to 1. So this is equal to 2I by 3 minus 1 by 2 minus I by 2 plus minus 2 by 3 minus I by 2 plus 1 by 2. There is minus 1 by 2 and there is plus 1 by 2. This gets cancelled off. I hope I have not made any mistakes here. 2I by 3 minus I by 2 minus I by 2. So it's basically 2I by 3 minus I minus 2 by 3. That's equal to minus I by 3 minus 2 by 3. This is what I eventually end up getting. Minus 2 by 3 and started checking what I've solved previously. So yeah, sorry. How come 0 to 1? Is that your question? Okay, just a moment, I'll tell you. I think I made some mistake in solving the previous part. This was pretty obvious though. Just a moment, huh? 1 plus IY. Okay, minus 1 minus IY. So when I integrate, what I get is this gets cancelled out, minus y cube by 3 plus IY square minus y cosine. This is IY square by 2. Alright. 1 gives me I by 2 and here it gives me minus 1 by 3. Okay, that seems okay. What about here? It's going along x from 0 to 1. X cube by 3, 1 by 3. Okay, I'm not able to figure out what mistake I made here. There is some mistake. Okay, so what was your question again, Sanjeev? How it comes 0 to 1? So here the limit is 0 to 1 because I have to, so this is my path, right? This red colored path you can see here, path number 3 that I marked. That is my path. So when I'm going along that path, um, firstly I have put up the equation y is equal to x because that is the path along which I'm following, right? Y is equal to x here. So when y is equal to x, uh, I've converted the whole integral in the form of dy only. Sorry, in the form of dx only. It has only x and dx. So when I convert it to dx, what is the change in the value of x? X goes from 0 to 1 in this path. Along this path, x goes from 0 to 1 only. We are talking specifically about x only now because the entire integral is written in the form of x, in terms of x. Is that okay? So the whole point behind choosing a path is just so that I can convert the integral into only one particular form. Generally, it will have both x and y because I have to integral over z is equal to x plus iy. That's my complex number. So when the integral is running over dz, I will have to use both x and y simultaneously. But if I know a path and if I know the equation of that path, I can simplify that. I can just substitute the equation of the path inside my integral equation and I can solve it in terms of one variable only. So that is what we are trying to do. We have this complex integral z square minus z, but because it is along the path x equal to y, it is along this path, red colored path, where x and y will be equal. It will always be x plus ix form. So that's why I'm using that equation and substituting everything in terms of x only. Now I don't need to think about y. So how is x changing? X is changing from 0 to 1 only. So that's why my limit is 0 to 1. Sanjeev, right? Okay. All right, all right. But here apparently I think there's a mistake made. X square minus y square plus 2ixy minus x plus iy. So y is 0, 0, 0, 0. So x cube by 3 minus x square by 2. So in this case what I get is 1 by 3 minus 1 by 2 minus 1 by 6. This is correct. No issues here. Multiplied by dz. Oh, I think the mistake that I've made is that I've forgotten the I outside. Hmm, I think that's what I've done. So because I've forgotten the I outside, this integral is all correct. I just have to multiply this with I. Because that's what I remember. When I solved this, I remember that this was coming out to be a function which is path independent. The integral is path independent. So that's what I'm wondering. It should not have come differently. Okay, so minus y cube by 3, I y square minus I. Okay, so I outside. So this is minus I by 3 and minus 1 by 2. Minus 1 by 2. So here my answer is minus 2 by 3. Let's see if that's what happens here. 1 by 2 plus 1 by 6. What is it? 6 plus 2, 8 divided by 12, which is 2 by 3. Perfect. So now my answer becomes minus 1 by 6 minus I by 3 minus 1 by 2 is equal to minus 2 by 3 minus I by 3. This is my answer. So yeah, you can see basically that along both these paths, what we did was we went along path 1, we went along path 3. And along both these paths, I got the same answer. So you should also check with path 2 for better practice. Try and check with part 2 also. You should be getting the same answer here. In this case, I1 is going to be same on all paths. So I'm kind of telling you the answer also for the first thing, for I1 at least. Now you do the same thing for I2 as well and check whether you're getting the same answer along all these three paths. You should have gotten a fair hang of how to solve this. You have to assume the equation of the path, simplify the integral accordingly, and substitute appropriate limits. Because if you are converting the whole integral in terms of x, then substitute limits of x only. If it's in terms of y, substitute the limits of y only. Is there any doubt here? If there is a question on how to do this integral, I can show it to you again. You should be clear with how to solve a contour integral using these first principle methods. So please, if there is any doubt, ask right now. Sanjeev, Naganthini, sorry, Nagananthini, my bad. No doubts? Okay, all right. So this is done. Question 2, you can solve the remaining part and choose the appropriate option. Now we'll move on to question 3. Here you have to solve for both. In question 2, you have to solve for both the integrals and choose one of the correct options. So yeah, you can do that now. All right, so what is the question? Evaluate the integrals. There are two integrals given where C1. So here in the first integral, the contour used is C1. We can see below the integral sign. The contour used is C1 and C1 is the circle mod Z is equal to 1. And so C2 is the circle mod Z is equal to 2. For the second integral, the circle that we're using is mod Z is equal to 2. And both of these contours are in the anti-clockwise direction. So the contours are like this in the anti-clockwise direction. So I am drawing, this is mod Z is equal to 1 and this one is mod Z is equal to 2. Both are circles centered at the origin. Okay. Now they're asking which of the following statements is true. I1 is equal to 0 and I2 is equal to 0. So, okay. So I think here there's a printing mistake. Of course, this one is I2, not I1. So they're asking whether I1 is 0 and I2 is 0 both, or I1 and I2 have some value, or one has some value, one is 0, vice versa. These are the four options given to us. So here, seeing this structure, we know what to do. We know Cauchy's integral theorem. So what does Cauchy's theorem say? Cyclic integral of f of z divided by z minus z0 is equal to 0. No, actually it's 2 pi I f of z0. We are assuming here that z0 lies inside this region, inside this contour region along which we are integrating. So when z0 lies inside the region, then this is what we get. F of z upon z minus z0 integral is 2 pi I into f of z0. Also, the assumption is that f of z is analytic in the domain that we are considering. In the domain where we are performing this integral, f of z has to be analytic. then only this is applicable, by the way, of course. So f of z is analytic. So this is what we know. Sorry, dz. Yes, yes, yes. Dz. Sorry. So yeah, of course, when you're integrating, it will be the integration will be along dz. So yeah, so z0 lies inside the region. But what if z0 does not lie inside the region? In that case, what is the answer? When z0 is not inside the region, then what is the answer? Hmm. So the answer is 0 when z0 is not inside the region, when z0 is outside. So basically, the whole function is analytic in that case. Here, for Cauchy's theorem, there is one pole at z equal to z0. So because of that pole, we are getting the integral to be something non-trivial. Otherwise, if there is no pole, if the entire function within the integral sign is analytic, then the right hand side gives you 0. For a function f of z dz is equal to 0 if f of z is analytic in the region considered. So here, of course, I'm including the z minus z0 part inside f of z itself for the second one. Here, when I'm writing f of, I should maybe let me write g of z. So basically, g of z is equal to, maybe let's say it's f of z upon z minus z0. But here, in this contour, the contour being covered by this, z0 is not inside that contour, inside that region covered by the contour. So in that case, it will always give me 0. So that's the only thing to be used in this problem. So I1 is sine z upon 2z minus pi. The function is same. Even for I2, the function is the same. Just that the contours are different. For the first one, the contour is C1. For the second one, the contour is C2. So will that make a difference? As we saw, it will make a difference because for the circle, mod z is equal to 1. Okay. For the circle, modulus of z is equal to 1. The pole is z0. If I want to say, uh, now my function is sine z divided by 2z minus pi, right? Yeah. 2z minus pi dz. And this is some contour. So I'll rewrite it like this: sine z divided by 2 into z minus pi by 2 dz. So my pole is at z equal to pi by 2. So for the circle, there are two contours to be considered. One is the circle centered at the origin and radius 1. And the second contour is circle centered at origin and radius 2. So for the circle centered at origin and radius 1, for mod z equal to 1 circle, z equal to pi by 2 lies outside. So in that case, the value of the integral is 0 if I am going around that contour. But for the second one, for the second circle, z equal to pi by 2 will be within this circle. Why? Because what's the value of pi by 2? Pi by 2 is something approximately 1.57 ish. So it lies inside the circle z equal to 2, mod z equal to 2. So in that case, you know how to evaluate it. You know how to use the Cauchy's integral theorem. So we'll use this expression 2 pi I into f of z0. We'll substitute that value and see what the value comes out. That's how you solve this. I'm not solving the whole question again because it's your job to do so. But I just gave a good flavor as to how to do this. So for the fourth one also, the idea is very similar. Let's do this very quickly then. We don't need to spend more time here. This is similar only. So for this one, all we have to do is carefully consider the contour, because again e raised to power 3z is analytic. Z minus ln 2, that's the only pole that can uh, you can have a pole at that point only, z equal to ln 2. So again you are given some contour, and all you have to do is check whether the point z equal to ln 2 is within the contour or not. So what is the square? Square is the c is the square with vertices plus minus 1 plus minus I. So it's 1 plus I, 1 minus I, minus 1 plus I, minus 1 minus I. These are the 4 points. So suppose this is my axis. Um, this is 1, this is I, this is minus 1, sorry, minus 1, minus I. Let me draw this like this. Okay. So this is the contour that we are considering, because the points are 1 plus I, 1 minus I, and such. So this is 1 plus I, this is minus 1 plus I, this is minus 1 minus I, this is 1 minus I, right? So this is the contour that we are considering, and z equal to ln 2. Then we have to check at what point is z equal to ln 2 lie. And we know that z equal to ln 2, the value is what, 0.3? I'm not sure. Let me check. No, 0.3 sounds wrong. 0.69 ish, right? Let me check nonetheless. Ln 2. Yes, 0.693. Ln 2 is 0.693. So that will lie somewhere here, zero point 0.7 ish. So because we know that the pole lies inside, you know what to do next. All you have to do here is just check the pole. Where does the pole lie? If it's lying inside, then you have to use the other theorem where it's 2 pi I into f of z0. Otherwise, the contour integral will become 0. Simple. No complication here. Any doubts? Okay. So here, what's the question? Fifth question is, for each of the functions f of z below, we wish to compute the integral I is equal to contour over C f of z dz, where C is the circle of radius unity centered about the origin. So the contour is again a circle of radius 1, and the center is at the origin. And you have to evaluate this integral f of z dz along this contour. The path being traversed is in the positive sense, which means anti-clockwise direction in the positive sense. Mark all the cases where I is equal to 0. So there are many different questions here, many different subparts here. You have to mark all the cases where the integral value is 0. Okay, so how do you do that? It's Again, as simple as that only, we have to just check where the pole lies. Firstly, before that, you have to check whether the numerator f of z is analytic or not. If it's not analytic, then doing any of this does not make sense. You just don't have to see the denominator and get done with it. First, you also have to check whether the numerator is analytic or not. So, in the first case, z square divided by z minus 3. Here, clearly, the numerator is analytic. Z square function is analytic. We know that already. Z minus 3 is the pole, but this pole lies outside the circle of radius unity. So this would be one of those cases. So you would be marking a tick here. For the second one, z e raised to power minus z. For this function, z e raised to power minus z, the whole thing is analytic, right? Z is analytic, e power minus z is analytic. The product is also going to be analytic. So this entire function is analytic. So in this case, what do you do? Again, I is equal to 0, right? In this case also I is equal to 0. So the point being, this is how similarly you will be checking for the other cases as well. Uh, I can see most of these problems are doable. For whatever is not doable, we can actually manually go about solving it. So for example, let's take the last question. It seems a little tricky. F of z is equal to log z plus 2. How do you do this one? How do you solve this one? So what we can do is, let's write z is equal to e raised to power I theta. Why can I do that? Because the contour is a unit circle with center origin. So I can write it as z equal to e power I theta. No r required. R is 1. So that's how I'm writing z. So this is simply equal to cos theta plus I sin theta. So then f of z is equal to log 2 plus cos theta plus I sin theta. Now let's redefine some z prime, or let's call it z1. Let's call it z1, which is 2 plus cos theta plus I sin theta. This is my some new kind of a complex number. Even this one I can call as r1 e raised to power I theta 1. Even this complex number z1, I can represent it as r1 e raised to power I theta 1. I can do that, right? So what would be r1? R1 would simply be square root of x square plus y square. So 2 plus cos theta the whole square plus sine square theta, and theta 1 is equal to tan inverse sine theta divided by 2 plus cos theta, right? So now substituting this inside log r1 e raised to power I theta 1, f of z is that, f of z is this. So this is equal to log r1 plus I theta 1 is equal to log square root of this function 2 plus cos theta the whole square plus sine square theta. So because it's a square root, the product that you get outside a square root is always positive, right? You know that square root of 4 is mod 2, basically. Mod x you get outside. You don't need to write mod 2, but basically square root of x square is equal to mod x. Square root of x square is equal to simply mod x. So you don't write square root of 4 as minus 2. You always generally write square root of 4 as 2. That's how it's defined in the complex plane. So when I'm writing a square root, the output that I get is going to be modulus, absolute value. So logarithm of an absolute value is well defined. For negative values, it's not defined. So here, for any value of theta, log is going to be defined. So this is going to be analytic. This function is analytic, the first part. The second one is I theta 1, I into tan inverse sine theta divided by 2 plus cos theta. Even this is analytic. It's tan inverse, and this is also going to be analytic. So all in all, the point is that this whole function f of z, which is log of z plus 2, is analytic. So because this whole function is analytic, you do the contour integral, and that's what you end up. You will end up with 0. So that's all you're supposed to do here. That's all you have to check. For the other functions, you do it yourself. I gave you a flavor using 3 functions. For each of the functions f of z below, we wish to compute the integral I is equal to, again, contour integral f of z dz, where c is the square whose sides lie along the lines x equals plus minus 2 and y equals plus minus 2. And the path is being traversed in the positive sense. So again, anti-clockwise direction. Mark all the cases where I is equal to 2 pi. This cyclic contour integral, this contour integral has to closed contour integral basically. This closed contour integral is supposed to give you some non-trivial value, a value of 2 pi. So that's what we want to see. So here you'll have to do both. You will have to check whether the pole lies within the contour, and you have to evaluate the value of the function as well. Both you will have to do. Okay, so but still it's not something difficult. So again, I'll not be solving all the parts. Mm, let's see. The first part looks trivial, so I'm not going to solve it. The second one, cos z upon z into z square plus 8. Mm, okay, okay. So the second question, cos z divided by z into z square plus 8. Here we can see that there are three poles, z equal to 0, z equal to plus 2 root 2, and z equal to minus 2 root 2. There are three poles here. But how many of them lie inside this contour? Z equal to plus 2 root 2 and minus 2 root 2 both won't lie inside, because this is 2 comma 0, this is Actually, I shouldn't be writing like this. I should write 2, yes, only 2. Here I should be writing 2i minus 2 minus 2i. Right? This is what, yeah, so these are the lines. So inside of this, you will find only one pole of this function also. Only z equal to 0 lies inside. Everything else lies outside. So you can use that idea to solve accordingly. Third question, z divided by 2z plus 1. That's also doable, pretty much doable. Final question, the fourth one is f of z is equal to cos z divided by z raised to power 4. So for this, what do you do? The power of z, the power of the pole, z equal to 0 is the pole, and it's a fourth order pole. Fourth order pole. So we use the higher order, uh, the Cauchy's theorem corresponding to higher order poles, right? So we know that f of z divided by z minus z0 raised to the power of n plus 1 dz cycling integral. This is equal to what? This is 2 pi I divided by n factorial f of n z0. Is this correct? You've seen this form, right? It's of course covered in the lectures. Yeah. This is going to be f of, yes. So this is okay. No mistakes here. So then what does this become equal to? Because n plus 1 is 4, n is equal to 3. So that's why the result that I'll be getting is 2 pi I divided by 3 factorial into the third derivative of z, and the value that you put in is z0. Z0 is 0 only. So you have to differentiate cos h z function 3 times. So you know that that is pretty much doable. The derivative is sine, then again cos h, first sin h, then cos h, whatever. So you can do that and then substitute the value z equal to 0. So you can solve this one as well. 2 pi I by 6 and multiplied by this. Yeah, so pretty much doable. All right, so let's move on to the next question. Are there doubts here? This is, this will be 0, you're saying? Integration will give you 0? No, no, come again. I can't hear you clearly. Yeah, go ahead. So you differentiate this to thrice cos h, right? So that gives you sin h, cos h, sin h. And then in sin h you put up the value of z equal to 0. So you whatever you get is your answer. I think what you're saying is right. I'm not sure. I'm not sure I've understood it correctly. But if I have understood it correctly, what you're saying is right. But that's for you to solve. My idea was to just give you a flavor of how to go about doing this. So if you understood how to do this, this is what I've shown. If you understood what I've shown, then whatever the answer is the correct answer. I'm not telling you what the answer is. All right? All right. Let's move on. Okay. So the question is, let C be the circle or radius of radius 3. There is a typo here. Let's make this off. Let C be the circle of radius 3 centered about the origin and described in the positive sense. We define the function g of z equals cyclic contour integral 2s square minus s plus 2 divided by s minus z ds, the whole ds. The question is, mark all the statements that are true. This is an integral over some other variable s. Okay, and the complex number z is also inside, and you have to mark all these statements. Which of these statements are true? So here, by the looks of it, s is also a complex function because we are going about practically solving ds. Uh, okay, right. So C is a contour in the uh, S plane, right? In the S plane only. So S is also a complex number here. C be the circle of radius 3 centered about origin. That's what we're doing. We are doing. And we are solving this contour integral over ds. So S is also a complex number. Z is also a complex number. There are two complex numbers involved here. But eventually, upon performing this cyclic integral over S, only Z will remain. So that is why left hand side is just a function of Z. I hope this much is clear. Why is it written that G? Why is it written on the left hand side that G is just a function of Z only? G will eventually be a function of Z only because after performing the integral over S, only Z will remain as the variable, right? I hope that's clear to you all. But S is also a complex number. So the contour integral that you're performing is also being performed on in the complex plane for a complex number. Okay. So having said that, now what you have to do is mark all the statements that are true. Once you define this kind of function, mark all the statements that are true. So what's the first statement? G of 2 is equal to 16 pi I. That's my first statement. So what I'll do is just give a flavor by solving only the first part. We'll see if we need to solve anything else, but only first part should suffice. So once you've done that, you can solve the other parts. So how will you solve G of 2? So G of 2 is simply, I'll substitute a 2 instead of Z. 2s square minus s plus 2 divided by s minus 2 ds. This is a contour integral. So again, this is something standard. 2s square minus s plus 2 is an analytic function. And s minus 2, there is a pole here. What's the contour? The contour is a circle of radius 3. So s equal to 2 will lie inside this contour. So you know how to go about solving this. This is simply 2 pi I f of 2, where f of z is equal to f of s is equal to 2s square minus s plus 2. So f of 2 is what? 2 into 4 minus 2 plus 2 is equal to 8 minus 2 plus 2, which is 8 itself. So therefore, g of 2 is equal to 2 pi I into 8 is equal to 16 pi I, which is the answer. So this one is the correct statement. Similarly, for g equal to 4, g of 4, you will substitute z equal to 4. For g of 1 minus 3i, you will substitute z equal to 1 minus 3i, and so on and so forth. So no complication here as such. This is a very straightforward problem, right? Any questions? Yeah. Difference between z and s. They are just complex numbers. Z is a notation generally we use, but now if I want to denote some other, both are complex numbers. They are two different variables, that's it. But both are complex numbers. Yeah, you can simply think of it like your z is say x plus iy. You could have written another complex number with x1 plus iy1, where x1 and y1 are also variables. So you can define another complex number, right? So similarly, s is just another complex number. It is residing in some other complex plane. Z has its own complex plane, has its own complex plane. Just two variables, that's it. Is that okay? All right. So question number 8. A function f of z is analytic within and on a simple closed contour C, okay? And z0 is not on C. We are told that f of z is analytic within this contour and on the closed contour C. And z0, which is a point here, in both these functions you have z minus z0 in the denominator. One is z minus z0, another is z minus z0 square. So in both of these functions, z0 is in the denominator, and we are told that z0 does not lie on C. Whether it is inside or outside has not been told. But what they're saying is z0 is not on C. So now study these two integrals, study the two contour integrals, and mark the correct statements. What they're asking is whether I1 and I2 both are going to be same if z0 is outside the contour, whether they are same if z0 is inside the contour, whether they are same generally, or whether they are same only for certain functions, very specific functions. So we are supposed to find out what's the nature of I1 and I2, whether they are same or not. Okay, so let's go about doing this. Hmm, Suppose z0 is inside contour C. Suppose z0 is inside the contour C. Okay, we are told that f of z is analytic, which means f prime of z is also analytic, right? Because analyticity is a very strict condition. It's not just that f of z is analytic, so we don't know about f prime of z. F of z being analytic is a very strict condition. So f prime of z is also ensured to be analytic. We've done that in week 1 itself. Sir has explained analyticity and all quite well. So f prime of z is also, we can assume it to be analytic. That's a fair assumption. So f prime of z is also analytic. Then now suppose z0 is inside this contour. So in that case, what do we get? What does I1 become? If z0 is inside the contour, I1 becomes simply 2 pi I f prime of z0. That's I1. What about I2? In the same scenario, what does I2 become? This is z minus z0 square. I2 z minus z0 square, which is z minus z0 raised to n plus 1. So n becomes 1. So we know that 2 pi I divided by n factorial into f of n z, z0 where n is equal to 1, right? So this is 2 pi I divided by 1 factorial, which is 1 itself, and f1, which is f prime. So f prime z0, that is I2. You can clearly see that I1 and I2 are both equal. Both are 2 pi I into f prime of z0, right? So when z0 is inside the contour C, inside of the region covered by contour C, when z0 is inside, in that case I1 is equal to I2. Now when z0 is outside, in that case what happens? Are they equal or not? Sorry. How? Both are 0, exactly. So here when it's inside, we've proven that the value that we get is the same. When z0 is outside, both the integrals give you 0. So that's why I1 is always going to be equal to I2. When z0 does not lie on C, I1 is always going to be equal to I2. So this is the option that you choose. I hope you understood the entire argument here. All right, so this is your question. Did I miss something? No. So let C be the unit circle centered about the origin and described in the positive sense. Again, the center is at the origin and the circle is described in the positive sense. Compute the integral e power az divided by z dz. C is unit circle. Okay. A is an arbitrarily real constant. We are told that A is real. Okay. Uh, so what they're saying is they're giving a hint in the question itself. Writing z equal to e raised to power I theta. Why can we do this? Because the contour that we are talking about is a unit circle centered at origin. So that's why I can write z equal to e power I theta when I'm going about that contour. So writing z equal to e power I theta, recast the above contour integral in the form of a real integral. So we can split it into two real integrals and I can come outside. So that's what they're telling us to do. What is the value of the integral? Only one part of the, so they are telling us some part of the integral. So we are asked what is the value of this part? What is the value of this integral? So let's solve this. Um, Directly by using Cauchy's theorem, we know that integral e raised to power az divided by z dz over the contour C, where a is real. So e raised to power az is analytic, is always going to be analytic. And because there is a z in the denominator, there is a pole, a simple pole at the origin. And because the contour actually includes the origin, so we know that how to, we know what's the answer of this integral. It's simply 2 pi I f of 0, which is simply 2 pi I, because z being equal to 0, e raised to power a into 0 is 1. E raised to power 0 is 1. So this is just 2 pi I. Okay. Now, what they're asking is writing z equal to e power I theta, recast this integral in the form of a real integral. Even when we do that, after doing that also, we should be getting the same result. The result should not be changing. I hope you understand this point. That of course we are, even though we are recasting this integral, it's the same integral that we are recasting in some different sense. So eventually the answer will still stay the same. So let's write z is equal to e raised to I theta and put it here. So it's a cyclic integral e power a into e power I theta, because z is e power I theta. So in the exponential there is an exponential term, e power a e power I theta divided by e raised to power I theta into d of e raised to power I theta. Now this contour integral basically in terms of, will come out in terms of theta, 0 to 2 pi. So theta will go in a full circle from 0 to 2 pi, and that's your cyclic contour. That's it. Is equal to integral 0 to 2 pi e raised to power a cos theta plus I sin theta. I'm splitting e power I theta in terms of cos theta plus I sin theta divided by e raised to I theta multiplied by I e raised to I theta d theta. So this gets cancelled. So integral 0 to 2 pi d theta e raised to power a cos theta multiplied by cos of a sin theta plus I sin of a sin theta. Do you understand what happened here? I had e raised to power a cos theta multiplied by e raised to power I sin theta. I had two terms here, e raised to power a cos theta, e raised to power a I sin theta. So now e raised to power a cos theta I took outside, and this is basically e raised to power I into a sin theta. So I'm just taking this as some simply e raised to power I x. So cos x plus I sin x, where x is a sin theta. Yes? Okay. So that's how we split this. And I know that the value of this integral has to come out to be 2 pi I. I know this already because I solved the integral. We solved the integral here, and we know that this integral should yield 2 pi I. Now, if you go to see, this is a purely real integral. This is, oh wait, we missed an I here. There's an I outside. So when I multiply I with this term, I will get a purely real integral. And when I multiply I with this term, I will get an imaginary part, right? I into integral d theta e power a cos theta cos of a sin theta, that's the imaginary part, plus the real part integral d theta e raised to power a cos theta. There is a negative sign actually, because I into I will give you a negative sign, minus d theta e raised to power a cos theta sine of a sine theta 0 to 2 pi. This is equal to 2 pi I. So what I'm saying is that this term will give me some real number because it's a real integral. And this term, the left term, just the integral inside will give me a real number, but that multiplied with I will give me a purely imaginary number. So because for complex numbers we can do this. Complex numbers, suppose I say x plus iy is equal to a plus ib. If this is equal, then x has to be equal to a and y has to be equal to b. This is necessary, this will happen. So similarly, when I'm saying that this part yields the complex, the imaginary part, and this yields the real part, this integration, so then I can simply equate this with the right hand side also. So I into d theta e power a cos theta cos of a sine theta is equal to 2 pi I, because it's just the imaginary part on the right hand side, and the real part minus of d theta e power a cos theta sine of a sine theta, this is equal to 0. So on the in the first term I will remove I from both sides, and this is my integral's value. So this is the integral that they've asked, d theta e power a cos theta cos of a sine theta. This is equal to 2 pi, but sorry, the integral limits are from 0 to 2 pi. For that the value is 2 pi, but what they've asked is 0 to pi. Okay, they've asked for 0 to pi. So how do you convert that? How do you convert that? Any ideas? Hmm, let's see if we can do this. I'm I'll have to think about this. Let's see. So I will divide this into 0 to pi d theta e power a cos theta cos of a sine theta plus, this is pi to 2 pi. So I am redefining theta prime is equal to pi plus theta. No, I am redefining theta prime as theta minus pi. So when theta goes from pi to 2 pi, theta prime goes from 0 to pi. So theta belongs to pi to 2 pi. In that case, theta prime belongs to 0 to pi. So for the second integral, I'm writing in terms of theta prime. Okay. So this is again 0 to pi only. D theta prime e raised to power a cos theta. So theta is pi plus theta prime. Pi plus theta prime sine of, no, cos of, what am I saying? Cos of a sine pi plus theta prime. D theta and d theta prime are the same. So there won't be any change in that case at least. I'll just write this term and see if I can figure out something. 0 to pi d theta prime e raised to power a e raised to power a cos pi plus theta prime. cos of pi plus theta prime is negative, right? Ha, 2 pi minus is positive, pi plus is negative. Okay, so this complicates things actually. E power minus a cos theta cos of a sin pi plus theta is also negative minus a sin theta prime. Okay, wait. Does that help? If I say the integral goes from minus pi to pi. Okay. So here generally, okay, so my bad. Here when we take a full contour integral in the circle, we generally the limits are from minus pi to pi. Let's see if that works. I think that should work out. So what I'm saying is the limit is minus pi to pi. So that's how we define the angle in the complex plane. It goes from minus pi to pi, right? So again, let's keep on doing that only. Minus pi to pi, minus pi to pi. So here it's 0 to pi, and here the difference would be that I want to go from minus pi to pi. So in that case, theta prime is just minus theta. So this is simply 0 to pi, 0 to minus pi, and minus d theta prime. I hope you are understanding what I'm doing here. What I'm saying is the limit is generally not 0 to 2 pi, it's minus pi to pi. So the integral that we have seen here, d theta e raised to power a cos theta into cos of a sin theta is equal to 2 pi. That integral is the limits are minus pi to pi. But what's asked in the question is 0 to pi. So how do we do that? So for that, for 0 to pi, what I'll do is I'm breaking it into two parts. One part is minus pi to 0 and the other part is 0 to pi. The 0 to pi part I've written first, and the second part is minus pi to 0. I've broken the integral minus pi to pi into two parts. One is 0 to pi and another is minus pi to 0. We can break that, right? That is an allowed thing. So I have written the first part as 0 to pi, and the second one I am writing minus pi to 0. But minus pi to 0, I'm converting the variable now. I'm changing the variable theta to theta prime, where theta prime is minus theta. So let's do that. Theta prime is minus theta. So how will I substitute here? The limits become minus pi to 0 becomes pi to 0 because theta is minus theta. And d theta prime is also minus d theta. So that's why a minus sign comes out here. Is there any doubt here? Should I explain this again? Please, you'll have to respond on this one because this may have been confusing. So someone tell me, is this confusing? Should I explain this again? Sure? Okay, okay, fine. So the limits are pi to 0 with a negative sign. When we flip the limits, the negative sign also goes away. All right, but let's do that later. Uh, and here, e raised to power a cos of minus theta prime cos of a sine minus theta prime. That's my expression. Now this integral I'm writing down. This is when I go from 0 to pi, when I shift the limits from pi to 0, I go to 0 to pi, there will be a negative sign outside, which will cancel this negative sign. So basically, there will be no negative sign also. This becomes plus 0 to pi d theta prime e raised to power a cos of minus theta is just cos theta. Cos of theta prime and cos of a sine of minus theta. Sine of minus theta is minus sine theta, but that is also inside cos. So again, that minus sign will also vanish. So what I get is cos of a sine theta prime 0 to pi. So this is exactly this. Both of these are exactly same, which is why what I'll claim is that the whole integral from minus pi to pi is simply 2 into 0 to pi of the whole integral d theta e raised to power a cos theta cos of a sine theta is equal to 2 pi. Therefore, 0 to pi d theta e raised to power a cos theta cos of a sine theta is equal to pi. Is this okay? Okay. Assuming that this is okay. Okay, so if you see the 10th one, let's copy this. So C1 denotes the positively oriented boundary of the square whose sides lie along the lines x plus minus 1, y plus minus 1. C2 is the contour, positively oriented circle, mod z equal to 4. Basically, uh, radius 4. The circle's radius is 4. Now they're saying study the two integrals I1 and I2. Functions are the same, just the contours are different. And for each of the functions below, mark all the functions for which I1 is equal to I2. So this is again very simple. Just the case where all you have to see is whether the pole is going to lie inside, outside both the contours. If it's lying inside one contour but outside another contour, then there will be a difference. Otherwise, it's going to be the same. That's all you have to see. All the functions. Yeah, you have to solve for all the functions. Yes. So you have to mark whichever is correct. Is that okay? Are we clear? Sure? Mm-hmm. Mm-hmm. Okay. So z plus 2 divided by sine z by 2. What's the pole here? What's the pole here? Sorry? 0, right? So the pole is at 0. Yeah. So pole is going to be at 0. So what can you do? So okay, let's try this one out. F of z is equal to z plus 2 divided by sine of z by 2. So z plus 2 divided by what's the Taylor expansion for this? Sine z. We can Taylor expand this, right? About the origin. So it will simply be z by 2. Bolo. It will be basically z. What's sine z Taylor expansion? It's z minus z cube by 3 factorial plus z power 5 by 5 factorial, etc. Right? Right? Agreed? Agreed or not? Right? Agreed. Yeah. So z by 2 minus z cube by 8 into 3 factorial plus z power 5 divided by 32 into 5 factorial and so on. So what I'll do is I'll take z plus 2 divided by z by 2 outside 1 minus z square by I've taken 2 outside. So 4 into 3 factorial plus z power 4 by 16 into 5 factorial and so on. Okay, so this is a polynomial function. Um, and the rest of these terms, okay, so I can just, what I can do is the rest of these terms, I can, this thing, it's just 1 minus z square by 4 into 3 factorial plus z power 4 into 16 into 5 factorial minus whatever raised to minus 1. So it is simply equal to 1 plus this whole term z square by 4 into 3 factorial minus z power 4 whatever this plus z square plus z cube whatever it will basically be a polynomial form. Do you understand this? What I'm doing is I'm simply yeah, I'm writing this in 1 upon 1 minus z form, so I can simply expand it out like this in the polynomial form. The polynomial form is always analytic, so this part one can forget what is happening here. Okay, it's a polynomial, but you don't need to think much. It is a polynomial in z square, so we'll have some huge function. And here outside I have a simple pole now. So 2 into z plus 2 into 1 plus this huge polynomial, which the least term is z square in that polynomial, divided by z. This is my function now, f of z. Is that okay? Yes. So now for z equal to 0, what you will do? Simply 2 pi I into 2 into z plus 2. Z is 0, 2. That's your answer. 2 to 4, 4 to 8 is equal to 8 pi I. For which contour? For both the contours. Both the contour contain z equal to 0. So for both the contours, the answer will remain the same. Is that okay? Is that okay? Yeah. So there is some other method also. Maybe sir will talk about it later. But there is another way to know that when there is sine z by 2 in the denominator, it's a simple pole of order 1 only. Here what we did is also that we kind of figured that out only. It's a simple pole of order 1. But if we don't know that, then it's slightly tricky to see whether how it's a simple pole of order 1. But here by this method we can figure that out. Fine. I hope that's clear. Okay. So similarly, other problems also you can, other parts also you can do. So yes, let me think. Is that the case though? Yeah. So we want to, when we wrote it in this form, we want to write it near the origin only. For every other point, we know that f of z is analytic because sine z by 2 is not giving you 0. Acha. By the way, you also should check for z equal to 2 pi, right? Next 0 will come at z equal to 2 pi. So z equal to 2 pi does not lie inside either contour. Z equal to 2 pi means 6.28 or something. The bigger contour is a circle of radius 4. So it is going to lie outside that. So the only pole of sine z by 2 is at z equal to 0 only. So that's why when we wrote it in this form, we are trying to figure out the order of the pole near z equal to 0 only. That's why this method is okay. Otherwise, writing 1 upon 1 minus z as 1 plus z square dot 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 is not valid if z is greater than 1, mod z is greater than 1. That in that case it's not valid. But we know that there is only one pole and that pole is near the origin. So what we are doing is we are doing this math near the origin only to try and figure out what's the order of the pole. So that's why near the origin this is valid, and we can do this, we can figure out the order of the pole. Once we figure out the order of the pole, we know the entire mechanism after that. Is that okay? Is that clear to you? Perfect. So that's the last question. Solve the other parts, and yeah, we're done for today. So thank you for joining. Yeah, yeah, tell me. Sorry, I can't hear. I can't hear you clearly. Yeah, yeah, tell me. Yes, yes, yes. So 40% marks from the assignment and 60% marks from the exams, final exam. So that is how your total 100 marks score will come. Yeah. So in a way, each assignment is of 5 marks because 8 assignments, 40 marks. So each assignment is of 5 marks. All right. Okay. Below 5 marks. I am saying each assignment is of 5 marks. So out of 10, it will be normalized. Your suppose you scored 8 out of 10 in assignment 1. So you will get 4 marks out of 5 in assignment 1. Similarly, the next assignment will be scored out of 5, and you will get 40 marks of the from the assignments, and rest 60 marks from the final exam that you gave. Fine. All right. All right. Anything else? Any more questions?